Welcome to this learning video. Using homogeneous coordinates, we can represent the translation, so the transfer or the move of a point in the three-dimensional space as a linear mapping. Think of a three-dimensional space with the coordinate system and an origin O, and consider a point X. The point X has, in this case, general coordinates X, Y, Z. So we now apply a translation vector t to this point. So it's like that from here to here, for example. This is also a vector t having three coordinates, for example t1, t2, t3. So this is a move of the point X to the tip of this translation vector, and the result then is this point, which is X plus this translation vector. So you can see this point X as a point, or also look at the positional vectors from the origin. So let's simply write down what's going on here is in mathematical formulas. So we have our point X, and this is mapped to X plus t. So we move the point X by the vector t. So the coordinates, the new ones are, you just add. Yeah. It's just vector addition here. In order to come to this point, you go first to X and then plus t, normal vector addition. And this is not a linear mapping, so it cannot be represented as a matrix A times the original vector X. Why? Because the translation here does not preserve the origin. If you would plug in here the origin 0, 0, 0, it should map also to 0, 0, 0. And here this is not the case. It's not possible. However, we would like to express it as a linear mapping, as a matrix vector product, because this would allow us to include translation within the set of linear transformations, alongside with rotations, reflections, and other operations, and then combine them easily. Why is this useful? Because when comparing linear transformations, because when combining linear transformations, we only need to multiply the corresponding matrices in the correct order. Remember, for example, we had first a reflection and then multiplied by a rotational matrix. You just have this composition, this multiplication of matrices. That's why we introduce so-called homogeneous coordinates, and with them we can represent this translation as a matrix multiplication, but in the four-dimensional space, so not in the three-dimensional space. So we have to increase the dimension. So instead of working with X, we define a new vector P by appending, so here it's the same, X, Y, Z, and here we append a fourth component, which we always set equal to 1. So what we're gonna do now is the following. We want a matrix vector product with this homogeneous coordinate P, which is X, Y, Z, 1 in the four-dimensional space, and we want to describe this translation. So this means we have X, Y, Z, but shifted by T1, T2, and T3. This is what we want. The last coordinate should stay the same. So specifically, we multiply the p vector by a suitable 4 times 4 matrix, and now we need to figure out what are the components, the entries of the matrix. So we know what is the result of the matrix vector product, which is here, which you can see here, and this represents the translated point in homogeneous coordinates. So what should this 4 times 4 matrix look like now? It has the following structure. So for example, let's start with the first row. You need here a 1, a 0, a 0, and a T1. So if you multiply now the first row with this column here, what do you get? X plus T1. Yeah. So now you also see what is the sense of this additional coordinate equal to 1. Next row, analogously, but for the y coordinate, and you shift by T2. For the z coordinate, you shift by T3. And the last one should just stay 1, so we have 0, 0, 0, 1. And this matrix we will call T. So the translation matrix in homogeneous coordinates. Multiplying this matrix T with the vector P gives us the translated point as desired. Now, how can we incorporate the geometric transformations? We have already seen like rotation around an axis or reflection across a plane through the origin. And how can we now incorporate the translations into this framework? Sorry, I mean, how can we incorporate these geometric transformations like rotation, reflection into this homogeneous coordinate framework? This is the question. So previously, such transformations like rotation, reflection, they were described by a 3 times 3 matrix acting on a vector x, y, z. To include these in the homogeneous setup, we embed this 3 times 3 matrix into a 4 times 4 matrix as follows. So you have a bigger matrix now. For sure, we need here the matrix A somehow, but we have to add one column and one row at the end to increase the dimension to 4 times 4. And here there are zeros, here is a 1, zeros. So and now let's do the proof. If you multiply by x, y, z equal 1. So what do you get if you do this? So for example, the first row here is the first row of the matrix A. And if you multiply by this x, y, z, the 1 is deleted and you just get the reflection or the rotation, the x corresponding x, in the next row y and z coordinate. And the last row will be just 1. So I just write it, but I will delete it afterwards. So you will get here, like here, this standard product, the 3 times 3 matrix product, and the last coordinate is a 1. But these are 3 components here. So this exactly matches the 3-dimensional transformation now extended to homogeneous coordinates. This embedding is quite elegant because it allows us to combine rotations, reflections, and now also translations into a unified framework of linear mappings, but now in 4D and not in 3D. Fine. So now let's look to an example. We want a reflection with respect to a plane which has the form x plus y plus 2z is equal 6. So this plane does not go into the through the origin. It does not contain the origin. If you plug in 0, 0, 0 here, you see it is not 0, it is 6. So this plane clearly does not contain the origin. So let's pick a point on the plane. For example, P is 1, 3, 1. So if you plug it in and check 1 times 1 plus 3 plus 2 times 1 gives 6. So this point lies on the plane. Now we want to reflect a point across this plane. So what is the first step? So the first step is we translate the plane to the origin. So you must move the plane to the origin. So this also means this point P must be translated, moved to the origin. And this is done with the translation matrix that shifts all points by the vector now -1, -3, -1. And it looks like that. So probably I write here the homogeneous coordinates, and then we have this matrix which has now this form: 1, 0, 0, -1, 0, 1, 0, -3, 0, 0, 1, -1, 0, 0, 0, 1. So the result then is the point x, y, z, if you multiply this out, minus p. So let me make a very quick sketch from the side. So here there is a plane from the side. Here is the origin, and the point P lies on the plane, and we now shift it in this direction. This is what's happening. So this was our first step: translate the plane to the origin. Now we can use our formulas for the reflection. So we reflect across the translated plane. Now the plane also passes through the origin, and we can apply the known reflection matrix for this plane given here. And we must embed the 3 times 3 reflection matrix into a 4 times 4 matrix for the homogeneous coordinates. And it looks like that. So this means I split it a bit here now. We have zeros here, a 1, 0, 0, 0, and here there is this reflection matrix A. Yeah, I write here subscript reflection. So this was step 2. But there is an additional step we have not finished, because we must translate back. Finally, we translate everything back by the vector 1, 3, 1. So it's a similar idea as you can see here. So let me write the matrix here, which is then 1, 0, 0, 1. And we shift it back with the vector 1, 3, 1. And the rest is the identity matrix, because we don't change anything. So this is the third step: translate back. So the final result here is a multiplication of these 3 matrices. This gives you the full reflection across a plane, not through the origin. implemented entirely as a linear transformation in homogeneous coordinates. The same method works for rotations around the axis that do not pass through the origin. Thanks for watching and see you next time.